Good. Hello, everyone. Thank you for connecting with us. We're still waiting for a couple of people, so we're gonna start the presentation in 2 or 3 minutes. We'll be right back. Hello, everyone. Hello. I'm kind of out of the set, but I'm Patrick Sheen. Nice to see you again. So we're going to start this presentation with Xavier, our Chief Scientific Officer. And so today we're going to talk about the lift technology and the brand new wavefront sensors that Imagine Optic is releasing. And you will have the opportunity to enjoy the first demonstration of these two wavefront sensors in action. But before we go into the demo phase, Xavier will tell us a bit more about the technology itself, how it works, and how we integrated it in those sensors. And we'll be joined for this session by our colleagues from the US team, Philippe Clemenceau in Boston and Jérôme Balesta in San Francisco. So I'll hand it over to Philippe to present Axiom, and he will also take care of the questions along with Jérôme. So this brings us to the Q&A session. You can use the Q&A tool in GoToWebinar in the little panel on the right side of your screen. You can also, at the end of the demo, raise your hands and I'll open your mic so you can speak your questions aloud. So I'm going to go back to my more COVID-compatible seat. And we're going to start this presentation. So after the introduction, we'll hear from Xavier and have the two demos, and the Q&A will take place afterwards. Quick word about Imagine Optic. We're a 25-year-old company. Actually, we're 25-year-old since, sorry, little technical issue. So it's our 25th anniversary this year, and the lift is kind of our birthday present to some extent. We're a company specializing in everything wavefront, from wavefront sensing to adaptive optics. We create and manufacture sensors and deformable mirrors, along with other systems that are used in optical metrology, but also in microscopy. And you'll find more about all these products and what we do on our brand new website with the HASO LIFT 272 in good position. You can also access the catalog with all of our products, along with a number of application pages, and brand new from this week, you can also use a little tool to create a pre-quote and pick up whichever product you would like on the website and get a pre-quote automatically and then get more detailed information from our sales department. So in the US, we have the chance to be represented by Axiom Optics, and I will hand over to Philippe in Boston.
Hello, Patrick. Hello, Xavier. Thank you. So yes, I think I'm the CEO of Imagine Optic Inc. and Axiom Optics. So, we're based in the US. We're a team of 6 people, and we're here to help, people in scientists, engineers from companies, national labs. I think a lot of the attendees here probably know us already. We are part of the Imagine Optic group, and we do, here on this slide, very quickly, we do a bit more than distribute the Imagine Optic products. We also have, like microscopy systems, scientific cameras, beam characterization, beam shaping, adaptive optics, and also positioning isopods. So this is kind of represents all our activities there, and we're very happy about this new development for the HASO LIFT, of course, and we welcome very much helping all the scientists and engineers who will want to know more here in the US on this. So now I guess this is the start of the presentation, and Xavier, I believe this is your time now.
Thank you, Philippe, and hello everyone. So yeah, I'm really proud to show you today our new Wavefront sensors and high spatial resolution Wavefront sensor, as we are going to see together. So let's have a quick word about our technology. Sorry. So some quick word about, first of all, standard Shack-Hartmann technology. So as you may know, Shack-Hartmann Wavefront sensor are actually measuring the local slopes of a wavefront. And how it works, it's the combination of a microlens array and a detector. And each little microlens take a part of the incoming wavefront, and depending the direction of this little part of the wavefront, the spot will be moving, focalized by the microlenses, and the position of the spot on the microlens array, or the detector, give direct access to the local slope in y and x axis, the local slope of the incoming wave. And thanks to an mathematical integration, we do have access to the wavefront itself. So let's have a look now at an Hartmann. What is an Hartmann? It is the raw data on the detector. And in this Hartmann, I've put high frequency contents into the wavefront, and in this configuration, the local wavefront intercept by each microlens cannot be considered as a plane, just a flat, a small flat portion of the wavefront. And it is obvious here when you are looking the spots, and for example, these spots or this one are not a perfect diffracted limited spot as this one. If you are looking at this one, this spot, you can see that you can clearly see the diffraction of the square geometry of our microlens, and you get a perfect PSF and diffracted limited PSF, and so we can consider on this microlens that the wavefront just in front of this microlens is quite plain without any high frequency, but for this one or this one, for example, it's clear that the spot is not symmetrical anymore. And that means that the local portion of the incoming wavefront in front of this microlens is not a perfect plane, but presents some high frequency aberration. And the idea here, and the idea of the list, is to use the information that are into the shape of all the spots of the Hartmann. That means that it is possible, thanks to a phase retrieval algorithm, to find and to calculate the shape of the wavefront that can explain the shape of the focal spot. And if we do that, we can improve and enhance a lot the spatial resolution, because during the reconstruction, the portion of each of the wavefront in front of each microlens will not be considered as a plane, but as a wavefront itself, a small portion of the wavefront itself. And that's the idea here, to show you the two steps of the lift reconstruction. The first step is to use, of course, the position of the spots in order to have the tilt of the incoming wavefront in front of each microlens, but to use also a phase retrieval algorithm working with only one image in order to have more than just the global tilt, but also the shape of the wavefront in front of each microlens. So if we can do that, for sure, we will enhance a lot the spatial resolution of the reconstructed wavefront. And it's what we are going to show you today. So just to show you the sensitivity of this kind of algorithm, I made a simulation of a perfect diffracted limited spot given by one microlens without any aberration in front of it. That's this image on the left. In the middle, I have made the same simulation, but I have had a very little astigmatism, 10 nanometers peak to valley. And on the right part of this slide, you can see the result of the difference of these two spots. And this difference exhibits a clear signature. And this signature is the signature given by an astigmatism. And now you know a lot about the lift technology. The lift technology is using the information of the shape of each spot, and the information given by these spots is found thanks to the difference between the actual spots minus the same spot without any aberration in front of it. Thanks to this difference, we do have the signature, and thanks to this signature, we are able to find the aberration. Just to show you a little bit more, I will. You can see here on this slide the signature of the first 9 legendary polynomials. We have chosen legendary polynomials because we are using square pupil, and on square pupil, these legendary polynomials are orthogonal, and it is very useful when we want to make a reconstruction to have orthogonal polynomials. So on the first line, you have the signature of a pure tilt in x-axis and in y-axis. On the second line, you have the signature of a pure defocus, a pure astigmatism at 45 degrees, and a pure astigmatism at 0 degrees. On the third line, you have an example of a third order polynomials, and where you can find, for example, the comma here for the x-axis and the comma for the y-axis. Excuse me. Okay, so I won't enter into the details about the algorithm and how it works. This phase retrieval algorithm works with only one image. But if you want to learn more about that, I recommend you to read these three papers because we are not the first working on this subject and trying to enhance spatial resolution of a Shack-Hartman system. The first working on this subject was people from Onera, and I recommend you these two paper from them, and they worked on this subject in 2014 and 2013. And with these two papers, you will learn more about this kind of algorithm. For sure, our work was to optimize and to push a little bit more the technology in order to enhance the resolution even further and to make it very quick. So let's have a look now about the improvement of the resolution. So as we wanted to prove the improvement of the resolution, we have developed this optical bench with a light source, a spatial light modulator, and two optical pathways. One optical pathway with a standard HASO that can be combined with the LIFT technology, and a second pathway with a zoom, 4x zoom with a standard HASO in order to see, let's say, we can say the truth. What we expect with our algorithm to improve the resolution by a factor of 4 in the two directions, so that is to say a factor of 16. So in order to prove this improvement in resolution, we have decided to realize and develop this bench with a zoom 4 time 4 with another wavefront sensor, and we are going to compare what is seen by the wavefront sensor with what is calculating with the standard technology, standard Shack-Hartman technology, and the LIFT technology. So the first thing we wanted to see is the transfer function of this wavefront sensor. So a very common way to calculate and to measure a transfer function is to put some sinusoids. So what we have done, we have put some sinusoids with different spatial frequency. We began with low frequency and finished with very high spatial frequency. Now let's see some example of this measurement. So let's begin with a low frequency, and the low frequency is, for example, 8 microlengths into a period of the sinusoid. So for the reference wavefront sensor on the 4x zoom, pathway, it's 32 microlengths. So with 32 microlengths, for sure, a wavefront sensor, Shack-Hartmann wavefront sensor can measure very, very accurately. And the amplitude of the sinusoid is 550 nanometers. And without no surprise, the wavefront sensor, the standard Shack-Hartmann wavefront sensor with this kind of spatial frequency give us the right amplitude and the right sinusoid, and for sure the lift technology give us the same value. So no surprise here. And now let's see the result with a much higher spatial frequency. And now the spatial frequency is 2 microlengths for one period of the sinusoid. So once again, the reference wavefront sensor with the zoom 4 time 4 give us the amplitude of the sinusoid. That has to be seen, and the amplitude is 100 nanometers. And when you are looking at the result of the standard Shack-Hartmann wavefront sensor and standard Shack-Hartmann reconstruction, you don't see anything, any signal. And why that? The explanation is there. The phase of the sinusoid is done like this. One part of the sinusoid in front of 1 microlength, and the other part of the sinusoid under the other microlength. And the phase of this one is done like this. The way it's done is that in front of the first microlength, we don't have any tilt, but only a curvature in one side, in one direction. And under the other microlength, we do have also no tilts, but only one curvature with the opposite sign. And in this configuration, there is absolutely no displacement of the spots, only a modification of the shape. So the standard reconstruction in this configuration doesn't give any signal because there is any movement of the spots on the detector. Now, if we are seeing this the lift reconstruction, what is the point here? There is no displacement of the spot for sure, but there is a modification of the shape of the spot. And thanks to the phase retrieval algorithm, the system is able to reconstruct this small curvature in front of this microlength and the curvature with the opposite sign on the other on the second microlength, and the result at the end give us the right amplitude with the right frequency for the sinusoid. That means that for this spatial frequency, we are at the limit for the Shack-Hartmann technology, but we are quite far from the limit for the lift reconstruction. So we have continued this measurement with all the spatial frequency, and you can see the result here in this figure. So in blue, you have the transfer function of the standard Shack-Hartmann technology, and in red, you have the same transfer function for the lift reconstruction. So what can we see here? We can, first of all, look at this spatial frequency, 0.25. And this spatial frequency is twice Shannon frequency for a standard Shack-Hartmann technology. And twice Shannon frequency, that means 4 microlengths in one period of the sinusoid. That's why it's 0.25. And we can see that for this Shannon frequency, we are quite close 1, but a little bit less, about 0.8. And it's the beginning of of decrease of the transfer function for standard Shack-Hartmann technology and standard Shack-Hartmann reconstruction. And we can see that for the lift technology, it's 1. And even at this spatial frequency, is the spatial frequency we have just shown before. It's 2 microlengths into a period. And for this spatial frequency, we are very close to 0 for the standard Shack-Hartmann technology and 1 for the lift technology. And when we continue, we can see that at this spatial frequency, that is to say 1 microlength, 1 period, 1 microlength per period, excuse me, we do have around 0.8 for the transfer function, and 0.8 is exactly the same value as the twice Shannon frequency we had for the standard Shack-Hartmann reconstruction. And between these 2 points, we just have an improvement of the resolution, a factor of 4 between these 2 lines, and this, the comparison of these 2 transfer functions show us, exhibits an improvement of a factor of 4 in one direction, that is to say a factor of 15 for the 2 directions, X and Y. Okay, excuse me. Let's have now the live demonstration of the system, and let's have a look of the bench I've just mounted for this webinar. So in this bench, for sure you will have you can find an optical source. So it's a single mode fiber with a diode fiber here. The light is collimated on the SLM here with this lens. So the SLM is controlled by this computer here, and with this computer I can put the hologram I want on the SLM. The light is coming back, and there is a beam splitter here, and the light is analyzed by this Wavefront sensor. It's a LIFT 272, and we will see the result. So the fact is, with the software we are going to use right now, the WaveView 4 software, we can use this Wavefront sensor both with the standard Shack-Hartmann reconstruction, but also with the lift reconstruction. So like this, we will be able to compare the improvement of resolution switching between the standard reconstruction and the lift reconstruction. So let's have a look now at the software. So I will share my screen.
Sorry about that.
Okay, I share my screen. So here we are in standard Shack-Hartmann reconstruction, and I have absolutely no hologram put on the SLM. So what we are seeing right now is the residual aberration of the optical bench itself, and we can see that it's quite good because it's about 20 nanometers RMS aberration, residual aberration. So the resolution here is given by the number of microlengths. So that is to say, it's about here 50 by 68, and what is lightened here, it's about 50 by 50 microlengths. And so the phase reconstruction gives us this 50 by 50 resolution. So now I will put on the SLM a standard target for measuring a transfer function. It is a Siemens target. So I put it as an hologram, a phase hologram. And now you can see it. And you see the result with this standard 50 by 50 resolution, standard Shackleton resolution. And once I will push this button here, the lift button, I will activate the lift reconstruction. So let's see the result. Wow, I love this. It's always amazing to me. And you can clearly see the improvement in resolution. You can clearly see that the sharpness of the target is much better. We are going much further inside the middle of the target. Let's try again. So without the lift reconstruction, standard reconstruction, and lift reconstruction. Once again, just for fun. Here it is. So we can clearly see the improvement in resolution, and I would like to show you a second image. And this second image is a natural image. And a natural image exhibits a full range of spatial frequency. And that's why I would like to show you that. And so I will put this natural image as a phase hologram on this SLM. And the natural image I've chosen for you is a monkey. So I will put the monkey on the SLM, and now you can see it. You can see the standard Shackleton reconstruction on the monkey. And now I will push the lift button to have the lift reconstruction. Here it is. I love this too. Let's do it again. So without the lift technology, standard Shackleton technology, and lift reconstruction. So you can clearly see in this natural image the improvement in terms of spatial resolution. And now the last image and the last hologram I would like to share with you is a more optical system. It's a diffractive element, a diffractive lens. So I put the diffractive lens here, so you can see the result of the diffractive lens with a standard Shackleton reconstruction. So we can count about 1, 2, 3, 4, between 4 and 5 steps on this diffractive lens. And now I will activate the lift. And in this configuration, we can count 1, 2, 3, 4, 5, 6, 7, and 8 level. And it's normal because we have put 8 level in this diffractive lens. Once again, without the lift, and so the standard reconstruction and the lift construction. And you can notice here that the value, the peak to valley value and the IMS value, so the peak to valley value is 150. And once I activate the lift technology, the lift reconstruction, we are closer the true value is more than 200 nanometers, and it's what I've put on this hologram. So I have now finished the live demo of this 272 HASO LIFT sensor. So I will be more than happy to answer some questions if you have some questions at this step, or unless I will continue to show you, or maybe we can see. Yes, maybe we can see the result with the big brother of the HASO LIFT 272. It's the HASO LIFT 680. So the spatial resolution of this one is 680 times 500 points, face points. And if we are looking at the result of, it's not done in live, but I've done before, we can see the result with a mandrill, with a monkey. Please, Patrick.
You can go ahead, Xavier.
Okay. No.
You should be able to go ahead.
No.
Okay. There you go.
Okay. So that's the result with this Wavefront sensor and much higher, even much higher spatial resolution, more than 340,000 face points. And in this, you have on the left part the phase hologram sent to the SLM. On the middle, in the middle, you have the standard Shack-Hartmann reconstruction, and on the right part, you do have the lift reconstruction. And if you compare the two, we are very close to what we have sent. And you have to know that the resolution of the SLM is 800 by 800, and here in this image, we do have 400 by 400 points, face points. So now, do we have question, Patrick? Or
Yes,
Yes.
there are a bunch of questions here.
Okay.
So I think it would be good to address. How much time do we have now to address questions? This is.
I would suggest taking like 5 to 10 minutes for these questions. Then Xavier would like to show you one last thing.
Yeah. Okay.
Questions.
I think it would be good. There's a question here that I think it would be good to, it's a general question about the trade-offs compared to the, the regular HASO Shack-Hartmann. So, but being more specific, I think about like, do you keep the dynamic range? Is the accuracy the same? I think there's questions about noise also. Does noise propagate? Also, because now you have a smaller element. There are questions about that. Sensitivity to tilt. Can you elaborate on that a little bit, Xavier?
Yeah, for sure. So you have to be aware that the LIFT technology is the combination of the standard Shack-Hartmann technology plus the phase retrieval done in front of each micron. That means that you have all the advantage of the Shack-Hartmann technology in terms of accuracy and for sure in terms of dynamic range. So we are not limiting the dynamic range with the LIFT technology. Okay. And the second question was about the sensitivity. So maybe I can show you in live. Please, can you share my screen again, please?
Yes, certainly.
Okay. So in order to show you the sensitivity, I propose you to show you the repeatability of the system. So I put in LIFT technology, and I am going to take a reference, just the last measurement. And now we can see the sensitivity of the system. And and we are about 2 to 3 nanometers RMS. So it's about lambda over 200, as we have in standard Shack-Hartmann technology. And what was the third question?
So another question is on the is this, so I think when we see this, it looks like it's just a software upgrade, and you only need the new WaveView software to have the, with the lift algorithm to obtain this resolution. But I already know that there's also a hardware difference on the HASO lift. Can you elaborate a little bit more on this, Xavier?
Yes, in order to be able to make this phase retrieval algorithm with only one image, we had to make several things in the hardware part. First thing was to optimize the design of the Shack-Hartmann, number of size of the microlens, focal length of the microlens, number of pixels per microlens, in order to have a sufficient number of pixels to make this lift and phase retrieval algorithm on the spot itself. And the second thing is, in order to have this kind of accuracy, it was necessary to make a special calibration for the lift part of the software. So that means that it's not possible just to take the software and apply it to any Shack-Hartmann wavefront. It won't work.
Okay. Another question quickly, how does the lift deal with low signal to noise? Maybe, in microscopy, for example, the signal to noise is very low. How does that influence the algorithm?
Okay, once again, I propose to show you in live this point. So I remove the reference. I will put, for example, the Siemens target, and on this part you can see how much I sent, how much flux is sent to the wavefront sensor. So here we are quite far from the maximum. So here is close to the full well capacity saturation of the detector. So in this configuration, we do have a perfect signal to noise ratio. So just look at this figure, and I will reduce it progressively. And in the same time, you can look at the result of the reconstruction, and you will see that we don't have much degradation of the reconstruction. Now we are at half the amplitude. So some of I continue to reduce, so you will it will appear some part in the wavefront measurement where there is no more light because we are under the limit, and here we are at about 10% of the full well capacity. So here we are working with very low light, and as you can see, we are in a room with light everywhere in order to have a good image of the video when I talk and when you want to see me. So we are in a very quite bad condition to make metrology, and even in this configuration with only 10% of the saturation, so poor signal in terms of amount of light, and ambient light with a lot of perturbation, let's say. We have developed something that is very robust because you can clearly see that the reconstruction is still very good. I hope it answers the question.
Sorry, if you have another question.
There's a few other questions if that's okay. Like, do you in the lift technology, like it's not clear, do you also use the information of the spot's position?
Yes, we are using the information of the spot position in order to have the local slopes, the mean slopes, let's say, of the wavefront in front of each microlens. Once again, you have to see this lift reconstruction as the combination of the standard reconstruction for low order, let's say, low order spatial frequency aberration, and an addition of the phase retrieval made in front of each microlens in order to have the additional information about the high spatial frequency.
Okay, and then another question quickly is like, why are the lift wavefront sensors restricted to 400 to 800 nanometers when the broadband wavefront sensor HASO BV can work from 400 to 1100?
Yes, it's just because of the trade-off on the design. As I told you just before, we need enough pixels to make this lift reconstruction with a very high accuracy. And for that, because of that, we are not able for the moment to propose a lift reconstruction on the whole band, wavelength band between 400 and 1100. And for the beginning, we have chosen to offer you the possibility to do lift in the visible range. But for sure, we will be able to do lift technology between, let's say, 500 and 1 micron. But the first sensor will come with the visible bandwidth.
Okay, I think, you know, you guys have a few more slides, right? I mean, there could be another Q&A if you want right at the end. Maybe we'll let you go through the extra slides, if that's okay.
Yes. Okay, so now I would like to show you some examples of application for this lift technology. The example we can see and we have already experienced with. And for sure, as we do have a lot of dynamic range, a very high accuracy, and a very good spatial resolution, we think that this wavefront sensor is perfect for freeform optics characterization. For sure, as we are using a Schack-Hartmann system that is not polarization dependent, this kind of system can be used and quite well used for meta surface and meta optics. As we have seen just during the demo, it's very useful for diffractive optics, DOE, or phase sheet, faceplate characterization. For sure, in terms of optical characterization and polishing characterization, thanks to the high spatial resolution we have right now with this lift technology, is just very well for middle and high spatial frequency characterization. Of course, as we do have this very high spatial frequency, it's well adapted for small defect detection and characterization, laser impact, for example, on mirrors, for example. And for sure, it is possible to use this kind of wavefront sensor for quantitative phase imaging. But more than that, as we wanted to have a large range of application for this new technology, we have decided to have this new wavefront sensor completely compatible with our Airflex2 system. So the Airflex2 system with this wavefront sensor is a self-illuminated wavefront sensor, and thanks to this, we do have several possibility and several applications, as you can see on this now on this slide. Excuse me. Oops. This one. So thanks to this, we sent the light from monomode fiber here to, for example, a concave mirror in order to measure the shape of the concave mirror, but it could be a parabolic mirror. We can make the characterization of a very complex optical system. For example, here a telescope. We enter with the right numerical aperture into the telescope, and we put a flat mirror at the output, and the light is coming back and is measured with the wavefront sensor. And thanks to that, we can have the high and middle frequency characterization, thanks to this lift, HASO LIFT technology. And for sure, it will be useful to use this technology for optical characterization of objective and lenses in double pass, in order to have more information about the aberration, but also more accurate measurement of the MTF if this optical element presents some high frequency aberrations. For sure, the MTF can be done on axis, but also off axis very easily, thanks to this optical module, the Airflex2. And the last thing I would like to show you now is the compatibility with the Airflex LA. So the Airflex LA is a collimator exhibiting a large diameter for the measurement. And as you can see here, we do have an Airflex LA here, and we can adapt this system thanks to a magnetic holder here. And with this system, you can do what you do with a standard HASO interferometer. That is to say, you can qualify a flat mirror, for example. And thanks to this lift technology, you can have this with very high spatial frequency measurement. More than 340,000 points with this wavefront sensor, for example. And with that, you can imagine doing what you are doing with a standard HASO interferometer, but you can do much better than that, because for sure you can have all the advantages of the Shackman technology. That is to say, that it's completely insensitive to vibration. We need only one image to make the acquisition. And the last but not the least is the fact that you can choose the wavelengths you put here. So you can have, for example, 630 if you want to be exactly at the same wavelength as the field interferometer. But if you have a mirror with a coating at, let's say, 500 nanometers, you can qualify it with a wavelength at 500 nanometers and get the result at the design wavelengths. And this is the main advantages compared to standard piezo interferometer. And at the end, you can see this as a multispectral interferometer. You can do all the application you will dream of with this system, like multispectral interferometer. And as it is not sensitive to polarization, you can even imagine to control the polarization here in order to have a characterization with the polarization you want with this system. So at the end, you can do what you do with a standard interferometer, but you can do much more than that.
So I think it's now time for more questions.
I don't see more questions here. Actually, okay, there was one question, so I'm sorry, about freeform optics. You mentioned freeform optics in the applications. In what way would you measure freeform optics? And the question is, can you measure surface form figure?
Okay. So freeform optics are quite complicated to measure, and what you need when you want to measure freeform optics, you need basically three things. You need a good accuracy because you want to have the real shape of your system. You need a huge dynamic because freeform optics often exhibits a large variation of shape compared to pure curvature, for example. And for sure, you need to have a high spatial resolution because the shape can vary very fast on small distance. And this wavefront sensor, the LIFT technology, offer you these three main constraints and main features that are required to make freeform optics metrology. And in order to have the shape of, for example, a mirror, a freeform optics mirror, for sure you can use this kind of system, the Airflex system or the Airflex ALA system here, in order to make the characterization of your optics that is, for example, concave. But you can also imagine to put this into on an hexapod, for example, and scan all over your sample in order to have the shape of your sample, thanks to stitching procedure, for example.
Another question, quickly, because I know we're running out of time. Can it work with non-monochromatic light?
Yes, it is. You have to know that the first researcher that have worked on this subject was for astronomy, and astronomy means star, and star means white light. So for sure, this technology can be used for large spectrum. I cannot show you here because I have a monochromatic light here. But what I can do in order to show you this ability is to, okay, I will share my screen again. Okay. So, okay. So as you can see here, I've put here the wavelengths I'm using on this bench, and the wavelength is 635 nanometer is red. And so I cannot change it for a white source here, but what I can do is I can tell the software that it's not this wavelength, but for example, 400 and 400, excuse me, 485, so 150 nanometers far from the actual wavelengths. And now we are going to see the result. Here it is. So you can see here that even in this very hard configuration where the true wavelength is 600 nanometers and the software thinks that the wavelength is 400 nanometers, it's working. It's because we have done everything to be something very robust in one end, and we have done things in order to be able to work with wide broadband bandwidth in terms of wavelengths. So here it's really a worst situation because we have a monochromatic light, and the parameter for the wavelength is far away from the true wavelengths. In the case where you are going to work with a broadband light source, we recommend to indicate and to give the parameter for the software in the middle of the bandwidth. So, for example, if you have a bandwidth between 400 and 600 nanometers, we recommend to put 500 nanometers here.
Thank you, Xavier. Any more questions, Philippe?
I think we're good. I think we're good.
Okay. So if there are no questions anymore, I'll take the opportunity to actually hand out a quick poll. Just 3 quick questions. It'd be nice on your side to answer them. So my first question is, would you like to receive a copy of today's presentation? Thank you for your participation. And I think I'm going to close this one. Our second question is, are you actively searching for a solution? And thank you for your answers. I'm gonna close it in a few seconds. People still responding, so I'm holding off. Okay, thanks. And lastly, would you like to receive more information about the LIFT series?
Yeah, and I wanted to point out that there's also a catalog that's offered here that people can download in the GoToWebinar interface. I don't know if everybody saw that.
It's in the handouts section.
Yeah, in the handout section, it's.
Okay, thank you very much for your answers and for participating with us today. actually, this is time to say goodbye. So, thank you for joining us.
Thank you, guys. Thank you very much. And thank you, everyone, for attending. And
Sorry, our next webinar will be in June, and we will announce the subject soon.
thanks a lot.
Thanks,
Contact us for more info.
Bye
See you.
bye. Thank you.
Bye, everyone. Bye-bye.